Hello, everybody. Thank you very much. My name is Daniel Dunbar, and today I'm talking about a dream of mine, which is developing a new architecture for building software. So for those of you who don't know me, I used to work on LLVM and Clang a fair amount before I kind of disappeared from working on the project. And one of the things I'm talking about today is what I've been doing in the meantime. So a little overview of the talk. I want to start by talking about compile time, Clang compile times, and then move to talking about how we build software today, how we compile our software. And then I'm going to talk some about llbuild, which is one of the things that I went off and built, and it's a framework for building build systems. And then finally, talk about this idea of a new architecture for building software. So to start with, compile time impacts all of us. We work on a large C++ project, and I think very frequently if we find ourselves waiting on the compiler and we would like builds to go faster. So Clang was designed from the beginning to be a very fast C and C++ compiler. That was a big part of the reason to write a new C front end in the first place. And the way that Clang tried to be a fast compiler was starting with having a tuned lexing and parse implementation. Then we did things like we focused very heavily on having a very low overhead O0 path. So we tried to make sure that the compiler didn't do any unnecessary optimization when you were trying to do O0. And we did things like fast instruction selection to try to make sure that we just optimized for having a fast build. We also did things like there was a completely redesigned PCH implementation in Clang. As compared to the GCC implementation of precompiled headers, Clang's implementation tried very hard to make sure that it pulled the minimal amount of data out of a precompiled header that you needed to actually parse your source. And then we also did some crazy things like we integrated the assembler into the compiler so that we could shave off the time of emitting the assembly source code and then loading it back into the assembler. And overall, this was very successful. So in the first version of Xcode that we shipped, which included Clang, what we found was that Clang was about 3 times faster than the GCC we were using at the time to compile code. So it was a lot faster. But over time, that lead has gotten less. Partly that's because GCC itself has gotten faster, but the other reason that it's regressed is because performance regresses over time. Performance regresses for a lot of reasons. Some of the reasons performance regresses are because features were added. As compared to that first version of Clang, Clang has added actual support for C++. It's added support for C++ 11 and 14 and so on. There's also been tons and tons of new diagnostics added to Clang. And all of those features make the compiler a lot better, but they also can slow the compiler down, even if it's just because there's more code and the instruction cache is less full. So the other thing that can happen is some of that initial tuning can break. So as a really silly example, I remember sitting down once with Chris and looking at the code generation for Clang's diagnostics engine. So the actual code that we were getting out of the back end for the diagnostics that we emit in the front. And Clang emits a lot of diagnostics, so this actually it goes into Clang's runtime. And we tried to reorganize the code so that the back end could eliminate as many unnecessary loads as possible. And that was actually a performance win, but tuning like that is very fragile. If somebody comes in and wants to change the diagnostics engine to simply add a new feature, they might not know why it was written that way, and that tuning can break. In addition, optimizing Clang is very hard. So for a number of years, I spent a lot of time looking at Clang profiles to try and find off ways to make it faster. And one of the things that you see in Clang is that there are very few hot loops. If you look at a profile of Clang, you tend to see that we spend a lot of time in string maps. We spend a lot of time in lexing tokens. But those are really just on the order of 2 to 5% of the runtime. And the rest of the time is kind of spread throughout the code base. And that makes it very, very hard to know where you should even spend energy trying to simply sit down and optimize. So not everything is bad. We have gotten some occasional big wins over time to bump up compile time performance. So in the way that we build the Clang that we ship to our users as part of Xcode, we enable link time optimization. And link time optimization speeds up Clang itself quite a bit. We also use something called order files. So on Mac OS, the linker has a feature where you can arbitrarily reorder the symbols in the binary, and we reorder them based on a little bit of PGO type data, and then that improves the startup time of the compiler, and it improves your instruction cache. And I believe it's about a 6% win in compile time. And then, of course, we've gotten some major new features like modules, which dramatically reduce the amount of work that the compiler has to do to parse the source code, and so that speeds up compile time. But in general, I would say that there have been fewer architectural wins to actually speed up the compiler as compared to the kinds of things that were put in originally. And as a result, this is some data very kindly given to me by Chris Matthews, which measures the O0 compile time on just a handful of benchmarks from LLVM's test suite. And this is over a couple of our releases of the compiler, and these basically correspond to years. And what you can see is that we've pretty consistently regressed performance between 5 and 10% year over year. Now, obviously, you know, on top of tree, maybe something bad happened, maybe that's just a bug we can fix. But the general trend is pretty clear. The compiler is getting slower. So this talk is kind of about improving compile time at a high level. And when people think about improving compile time for builds, a lot of the times the first thing people think of is distributed compilation. The compiler is running on a bunch of different CPUs on my machine. If I ran it on more CPUs, it would go faster. Another way that you can improve compile time for builds is by fancy caching. A lot of times when we build software, we end up rerunning the compiler, but the inputs haven't changed. Maybe I did a git stash and a git pop. And so if you cache the data better, you can just do less work. This is, if you manage to implement this cache so that it's distributed and shared amongst the team, so all of us build LLVM, a lot of times we're not changing all the source code, maybe we could cache that. That can really improve build times. So there's another way that you can improve build times, which is simply to do less work. And that's what this talk is about. It's not about distributed compilation or fancy caching. It's about finding ways to make Clang produce the same outputs, but with less work. When I say less work, I mean a lot less work. I'm not talking about optimizing individual functions in Clang's implementation. Ideally, what I'm talking about is finding ways to do order in less work, where in is kind of the size of your build. And so if we can do order in for each individual file, that can be a really big win. So you might think, how is that even possible? Surely we would have already done that. So here's a simple example. Clang calls stat an average of 324 times for each individual input file during its own build. So the same input file across the lifetime of the build, Clang will call stat average of around 300 times. This makes sense because typically a lot of source files include the same other source files, and those files include the same other source files. So you tend to see a lot of translation units end up including the same stuff. And of course, Clang has to cache those. But if you think about the fact that as the project grows, more and more of the files you include are also going to be shared, that has a little bit of a quadratic behavior in the size of the project. So what if I told you that we could make Clang 15% faster at type checking without doing any work at all? So something that I think many people don't know is that the Clang frontend can process multiple translation units in a single invocation. The driver won't let you do this. The driver will always call one front end per translation unit, but the front end itself can process multiple translation units in serial order. And if you do this, what Clang will do is it will share the file and the source managers. And the file manager has a stat cache built into it. So it will end up skipping those stats I was mentioned earlier. This is actually something that works today. You can construct an invocation of Clang where you pass fsyntax only to only type check, and you use xclang to sort of pass additional arguments down to the front end. So I'm really cheating here. I'm using the driver, but I'm invoking the front end with 10 source files. And if you profile this, this is what you see. So in this case, what I've done is I have a trivial Objective-C source file, which includes one of the large frameworks on our platform. And what I'm measuring is the time for one front end to process those 10 source files, the same source file 10 times, versus the time to run the front end 10 times. And what we see is that it's actually 15% faster to do it within one front end. If you have modules on, it's actually 85% faster. It's a huge speed up, because at that point, all the compiler is really doing is validating that module, and it only has to do that once. Here's another cool thing Clang can do. We have this feature in Clang called the Precompiled Preamble. This is used today in libclang for interactive editing in an IDE environment. And what this feature does is Clang will automatically build a precompiled header for the preamble of your source file, which is just the code at the top that includes other source files. And that's typically where a lot of the code is actually imported into the compiler. It's not through the body, it's through all the imports. And then when you send a query to libclang, it will automatically reuse that precompiled header if it detects that the preamble hasn't been changed. So if you're editing the body of your source code and you haven't changed the order of includes or you haven't included new files, we get all the benefits of PCH. This is another thing that you can measure by just sort of manually creating PCH files. So in this case, I grabbed a median-sized file from Clang, happened to pick CG cleanup, and I measured the time to compile at 0 using a precompiled preamble. And what we see is that if modules are off, this is actually, it's twice as fast to compile with having created a PCH for that preamble. Even if you have modules on for Clang's build itself, it's still a 15% win. So those are two things Clang can already do today to basically generate the same output, but with less work. So that sounds cool. Let's do it. Why don't we go ahead and integrate those into the build? It seems pretty straightforward. What we'll do is if we have shared compilation flags, then we'll just make sure we reuse the front end. And if we have some source file that you're editing over and over again, let's just automatically make one of these precompiled preambles and use it. And then magically builds will be faster. But we have a problem. And the problem is that we, as compiler engineers, don't actually have any control over how the compiler is invoked. The compiler is invoked through a command line which has been statically laid down by the build system. It's in a Ninja file or a make file or something else. And we can't change the compiler to do something different. So in the past, we've talked about maybe we could do a compiler service where the driver would sort of take in the command line and automatically spin up a service and daemonize in the background and farm out a request. And that would be a kind of a way to get around this limitation. But that has a number of problems, and it's never actually materialized. So it seems like there must be a better way. And this is one of the things that led me to go off and do something new, is that it drove me crazy that on Clang, we built this compiler which was capable of doing all of this fancy new stuff, but we didn't have any build system which was capable of driving it effectively. So I want to step back for a moment and talk about how software is built today. So I suspect that for most of us, the way we build our software is through this very traditional Unix compiler build system split, where the compiler runs as a separate process. And then we have some very primitive mechanisms for communicating dependencies between the build system and the compiler. So the build system tells us about our inputs and our outputs through command line arguments. We also have this mechanism by which the compiler can write out additional dependencies that the build system can ingest. We don't even have a real file format we use for that. We just write them out as a makefile format, and we force the build system to parse it. And then this is a fixed input and output pipeline. We only have a limited set of places where we're supposed to read and write data from. If the compiler wanted to cache data on the side, technically, we don't even have an agreed upon location to do that. So from a certain perspective, this is basically an API contract. This is a contract between the build system and us. And it's an API that we haven't changed at all in decades. The last major advancement here was this argument that let us send dependencies back to the build system. Now, this is where the LLVM dragon swoops in, because the LLVM dragon heard me say API. And on LLVM, we love breaking APIs. So what would happen if we were willing to break this particular API? How could we build software? So one of the things I want to mention is that the earlier examples I gave were really just the tip of the iceberg of things that we could do in the compiler. The reason why I gave those examples were because they are things that we can actually measure today. They work today, and we can measure that there is a theoretical speed up possible there. But there are a lot more things that we could do. The one is ad hoc lookup tables. If you think about the lifetime of the compiler throughout the build, there are many places where the compiler ends up computing some amount of information in every build that could be accelerated through a lookup table. And if we had a way to keep that lookup table around, that would make the build faster. But today, that would require us to serialize it out to disk and read it back in, and that would probably mitigate the speed up. So we don't do that. A more fancy thing is what I call early exit via output signatures. So we could implement in the compiler the ability to take a signature of the LLVM IR after it comes out of CodeGen. And if that signature is the same as the last time we compiled that particular file, then we can just skip the backend. We know we're going to get the same object file out. This is a really big win if you do something like you change a comment in string ref.h and all of LLVM wants to rebuild, but none of your object files are actually going to change. So we could just not pay the cost of the backend in that scenario. And then finally, we have even more complicated things like dealing with redundant template instantiations. We have a pretty good idea that we spend a fair amount of time throughout the build doing a lot of work for the same template instantiations, creating them, type checking them, generating the code for them, and then finally passing them all off to the linker so that it can get rid of most of them. And there's a potentially very large win if we could find a way to do that work once. So for all of these kinds of things, what we really need is the ability to evolve that build system and compiler API that I mentioned. And in particular, we need these changes to be really easy to make. If I can describe the kernel of an idea in a couple minutes, then we should be able to go and prototype an implementation in the compiler relatively quickly and see, is this actually a performance win? So you might be saying, well, what about the module cache, the cache we use for Clang's module implementation today? Isn't this an example of where we cached something effectively throughout a whole build? So it's true, Clang's module cache does solve this problem. It automatically builds modules whenever they're needed, and it will share the result across the entire build. And this was done without any build system changes at all. So if we can do that, why don't we do it more often? The reason why is this is really a non-example. This is not how we want to tackle these problems. And the reason why is there is a very significant implementation complexity in doing something like the modules cache. The modules cache has POSIX file locking in order to manage coordination. It has its own custom cache consistency management scheme. So it has to watch and understand when it needs to rebuild modules. And then there's not that many debugging tools for it. It also has to have its own eviction implementation. Because modules can be large, so you need them to automatically be removed to save disk space. But then that means that the compiler has some logic for automatically pruning them, and it has some tuning parameters. And finally, it's also completely opaque to the build system scheduler. If I start up a bunch of Clang invocations and they all want the same module, then from the build system's perspective, it's going to be blocked. It's going to be waiting for all of those, but it actually could be doing more work on the cores that it has. It just doesn't know that. So what would a more ideal model for building software be? To me, it seems that what we really want is some kind of flexible API between the compiler and the build system. And these are the goals that I see. So the first one, as I said earlier, it should be really easy to share redundant work. If we see a place in the compiler where we realize it's redundant throughout the lifetime of a build, we should be able to implement that quickly. And in general, what we really want to do is we want to optimize the compiler for the entire build. Most users, other than compiler engineers, don't actually care about object files. What they care about is they care about getting their final product out. And so that's the situation we should optimize the compiler for being fast at, is being fast at doing the entire build. And then conversely, we should be able to optimize the build system via a rich compiler API. So If there's a place where the compiler realizes that it could do some amount of work in parallel, it would be really nice if we could talk back to the build system and communicate with it so that we can, so that the job can basically be scheduled very effectively. And then the last thing that we need here is we need to make sure we still have consistent and debuggable incremental builds. One of the benefits of the current strategy is that we try very hard on the compiler to make this strong guarantee that the same inputs will produce the exact same object file out. And that's a very good basis for having reliable, reproducible builds. And so if we did a different architecture, we certainly would have to retain that. So the ideal model that I see is that we really need the ability to integrate the build system and the compiler together, and to think of them as just, there's one process, the process of building all of your software, and we should be able to look at it kind of holistically. What that requires at the very beginning is a library-based compiler, a compiler that has been architected so it can be used that way. And what we've seen is that Clang already actually has some of that. We already have, to some extent, a library-based compiler. The next thing we need is an extensible build system. We need a build system which has been designed with the idea that some of the tools it interacts with should be able to plug in more deeply than just as an external process. And that's something that we don't really have. When you use Make or Ninja, they're really expecting to call you via a subprocess, and there's a few ways we can interact with them, but not a lot. And then the last thing that we would need, even if we had this extensible build system, is a plugin for that. And so this is kind of what inspired me to go off and do something new, and that thing was called llbuild. So llbuild is a new C++ library for building build system. It stands for low-level build, and it uses LLVM's ADT and support libraries, and it follows the LLVM kind of library-based design philosophy where you have a number of components that are layered on top of one another. And we ended up open sourcing this last year as part of the Swift project because we use it in the Swift package manager as its own, it provides its own internal build system. We also use this in a product called Swift Playgrounds, which is an iPad application which you can think of as being like a REPL for Swift. It allows you to have a lot of Swift documents, and you can easily interact with the code and play around. One of the reasons why llbuild is interesting and is used there is because in this app, you don't actually have files. You just have documents in memory. And llbuild isn't inherently connected to a file-based build model, and so it was capable of handling that. And then llbuild also contains a Ninja implementation itself, and so you can use it to build LLVM and Clang just as you would use Ninja with CMake. And this is actually how I build LLVM and Clang when I'm building them as part of Swift development, and I've been living on it for a couple years. So one of the main goals with llbuild was to ignore the build description and the input language part of the problem. I didn't want to just design a new syntax as a replacement for CMake. Most build systems, somewhere inside them, they have a little engine that's capable of evaluating a dependency graph. And that engine is usually fairly simple. And what I wanted to do with llbuild was instead focus on building a really powerful engine, the most interesting engine that could be built, in a way that it could potentially be used by lots of different build systems. One of the things that I knew I wanted to do to make, to make a powerful engine was to support this idea of work being discovered on the fly. So very few build systems can support the situation where you're executing some task, and then during the execution of that task, you realize you need to do more work. And that's one of the things llbuild can do. Another thing I knew I wanted it to do was be able to scale up to millions of tasks. Because the goal was to be able to take our existing builds and partition them into much smaller pieces so that you could get better incremental build behavior, it really needed to be able to scale. I also wanted to do things like support sophisticated scheduling. So during a build of LLVM, for example, we have a lot of CPU-bound stuff running the compiler. We have a lot of I/O-bound stuff, like running the linker, which sucks in all the object files. It'd be really nice if we had an engine that was capable of scheduling that. And then the last one was to have really powerful debugging tools. My hope was that by factoring out this separate project, which just focused on being the engine, that would provide a reason to also build a lot better debugging tools at that layer. And then the last thing that this project needed was some kind of pluggable task API. Oh, wow. So I want to kind of go through the architecture very quickly. llbuild is built on this idea of a flexible underlying core engine. And you could think of this as kind of the LLVM IR equivalent, where it's designed to be this common denominator between the high-level things, the build systems, and the lower-level optimizations. And at this level, it's really just a library for persistent and incremental computation. And to give credit where credit's due, this is very heavily inspired by this Haskell build system called Shake. And as I said, it's pretty low level. The inputs and the outputs are really just byte strings at this level. There's not files. They're just strings of bytes. And the expectation is that as a client, you'll encode data in those if necessary. And then functions are completely abstract to this layer. And there's a C++ API that's used to communicate between the tasks. And then on top of this core, that's where you build your higher level build systems. So there's a Ninja implementation sitting on top of this core. There's an implementation for the package manager sitting on top of it. So to give an idea around what it would mean to factor out this kind of more minimal engine, I wanted to step through what it actually looks like. So as I said, the engine is this, it's a very minimal, it has a very minimal functional model of the world. And it has four basic concepts. So the first one is keys. Keys are kind of this unambiguous name for some computation you want to perform. A value is the result of that computation. Then there's a rule, which describes how to produce a value for a particular key. And a task is a running instance of a rule. And then tasks can request additional keys as inputs. So to give an idea of how these concepts map over, a key in llbuild roughly corresponds to a path on disk when you're using Ninja. A value roughly corresponds to the stat information, because from the build system's perspective, kind of what it mostly does is make sure that that file exists. A rule is very similar to a rule in those systems, and then a task is kind of corresponds to fork and exec, the launching of the process. So I'm going to step through an example of how you actually use the low-level API to do something interesting, and I wanted to use recursive functions as the example. So as I said, the core engine can be used for just general purpose computation. And recursive functions form this natural graph structure, just like builds form a graph, because you can think of each result as depending on its recursive inputs. And if we're talking about recursive functions, really fun recursive function is the Ackermann function. So this is the Ackermann function. It's recursive. It can call itself in one of two ways. One is just a simple recursion. And in this other way, it first calls itself once, and then it uses the result of that to call itself again. So to build Ackermann, what we do is we encode the Ackermann invocation we want to make as the key. We encode that integer result as a value. Then we take those keys and we map them to tasks using our rules. And then the tasks themselves implement the Ackermann function. So here's what it looks like in C++. We have a little simple wrapper struct. So this is a key. It just wraps an integer pair. That's the arguments. And then it has a couple functions to convert it to and from a serialized representation. Value is basically the same thing. It wraps a simple integer. Where it gets more interesting is with rules. So the way llbuild works is you give it a delegate. I mentioned earlier that it can handle this idea of work being generated on the fly. And the reason why it can do that is you just give it a delegate, and you give it a function that provides it rules when it wants them. So unlike a Ninja file where all of the rules are present in advance, from the engine's perspective, it just has a function to request rules as they come in. So in this case, our function just decodes that key, and then it will eventually create a task if it's requested. And then this delegate has some other stuff, like it can report to you if it found a cycle. So tasks are where the real work happens. The way that the task works is that the engine will call back into your tasks as interesting stuff happens. So when a task is started, you're notified. When the engine has computed a result that you asked for, then it's given to you. And when all of the inputs that your task asked for have been computed, then it tells you that you're done and you should complete. So here's Ackermann. Here's what we're going to do. At the start of our task, if we don't need any recursive results, we don't need to worry about it. If we're in one of the cases where we need to request an additional value, then we just go ahead and form the key, and we tell the engine that we want that. So in this second case here, what we do is we first have to request the inner value, because we don't know how to request the outer one until we've gotten back that first computation. So then when those values have been computed, the engine will call back into us. And if we're in one of these cases where we had to do some recursion, then what we do is we store that first value. And then if we happen to be in the case where we need to request an additional value, then we just call back into the engine and say, wait, I'm not done, I need more work. And so Ackermann is actually using this ability to compute additional work on the fly. And then when we get back that second result, we store it. And then in this case, we kind of just look through and we return the appropriate result based on whatever case we're in. And so to tie it all together, this is what actually driving it looks like. We create our delegate. We create an instance of the engine using the delegate. And then we can just ask the engine to build whatever value we want. And so if you actually execute this on an interesting Ackermann instance, this is what will happen. One of the fun things about Ackermann is that it calls itself a lot. And so even though the input values look rather small here, what this actually did was create about 300,000 different executions. And if you compare that to an LLVM and Clang build, that's actually 42 times more instances of calling out to a task than is run during a Clang build. So with that, I just very briefly want to go through what our current performance looks like. So this is the time for a full build on both LLbuild and LLVM as compared to the real Ninja. And what you can see is we're basically at parity. That makes sense because during a full build, most of the time is spent in the compiler. In a null build case where nothing has changed, LLbuild is still a fair amount slower than Ninja. We're about 2.5 times slower on building LLVM itself. And the reason why is that LLbuild always has a database behind it. And our current database implementation is not particularly efficient. We just sit on top of SQLite. And that's where most of the time here goes. The last aspect of performance is scalability. I mentioned it was designed to scale to large graphs. And the way that I validate this is simply by looking at our behavior as we go to larger and larger graphs. And Ackermann is a very good tool to use for this because it lets you generate synthetic graphs of arbitrary synthetic size. So this is a graph of our performance for different sizes of inputs, ranging from very small ones up to over 1 million nodes. And the real takeaway here is just that it scales linearly. Even at a graph with over 1 million nodes, the null build time is still well under a second. And the memory use is still, so the numbers are a little weird here, but this is actually 500 megs of memory use, which is still something that you can fit on a single machine. The last thing I want to get to is this idea of a new architecture. I mentioned we need a library-based compiler. We already have one in Clang. With LLbuild, we have the beginnings of some kind of an extensible build system. And the last thing that we need to try and take advantage of getting performance improvements the way I mentioned is this compiler plugin. So I wanted to walk through a very simple straw man for what this could look like. I don't actively work on Clang, and so this isn't really intended to be a real proposal, but it's an idea around how we could do it. And the focus was just what's the easiest path to vet this concept and see if we could get compile time wins this way. And what I think would be a good approach would be to try to design some minimal new protocol that simply allows you to control the compiler as a sub-process. So do something like use JSON to send and receive commands to one compiler process so that it could do things like run the front end multiple times at once. And then you would just share these subprocesses when they're available. So you would dispatch individual compilation requests to the subprocess, and then this gives us a good resilience model. If the subprocess crashes, you can just restart it. So here's what that would look like currently. So when LLbuild starts up, it has this lane-based model where it has a lane per core that it wants to build on, and it just assigns compilation jobs into each lane as they complete. And the idea I'm proposing is simply that we weld these together within an individual lane. So we would keep the idea that the compiler is running serially, but it would just have the ability to do multiple compilations within one long-running process. The benefits of this is that it immediately enables file and source manager sharing, which is something that we already have implemented in Clang as a possible performance speedup. This also amortizes module validation time, which was one of the really big wins that I showed. And in particular, it avoids the need to make the full compiler thread safe, because each individual compiler is still running just as it does today as a serial process. And then, of course, the last great thing is it gives us this new API to break. So summary, my belief is that this current build system and compiler split we should view this as basically a legacy API. And that there are some potentially large compile time benefits that we can get by evolving this API in the same way that we usually get when we break APIs. We don't break APIs because we're bored most of the time. It's because the belief is that that new API is better and it unlocks some functionality. And so I think the same thing is true here. If we change the API, we can actually improve the way we build software. So if you want more information, llbuild lives under the Apple organization on GitHub. If you want to run it as Ninja, you can invoke llbuild ninja build, or if you symlink llbuild to Ninja, then it will automatically realize you want to run it in Ninja mode. And you can use this to build LLVM and Clang. And there are some docs in tree here, and then the Ackermann example itself is implemented inside lib commands. That's it. Any questions?
Questions?
Really cool talk, lots to think about. One thing you mentioned is that you have better scheduling by looking at I/O and CPU bound thingies. How exactly would you do that?
So there's a couple ways. So I only talked about embedding the compiler in this talk, but if you think far enough ahead, you can realize that a lot of the other tools could potentially benefit by being integrated. So in theory, if both the compiler and the linker were integrated with the build, then they could just directly communicate to the build to say, here's how much data I read versus here's how much time I spent on the CPU. You can also do things like simply capture historical data and assume that's a good representation for the future. So that's how you would get the data to drive your scheduler. How you would actually then use that to implement a scheduling algorithm, I think depends a lot on what benefits you believe are possible. The big benefit that I believe is possible is not so much in active scheduling of the jobs you have, but in a forward-looking scheduler. So what you want to do when you build LLVM is you want to make sure you don't end up in a situation where you're only linking. Like, that's bad. You're going to thrash the disk. So what you want to do is actually much earlier schedule your compiler so that you can get to that first link so that you have more compiler work to do while that link is running.
So one of the problematic aspects of designing new API that I can think of is when you start combining different languages. So for example, when you have, say, Rust or Swift that can call into C function, do you think that you can design an API that can actually express those dependencies across languages?
Well, so the reality is the API we have today is very primitive. So you can certainly implement a new API and then only opt Clang into it and still get benefits because Rust works the way Rust works. Rust can continue to work the way it works today, right? You just shell out to it. So I think that I certainly think there's a big there's a lot of benefit in an incremental strategy where you just try and opt Clang in because the reality is there's a lot of C++ software that builds very, very slowly, and I think that would be a big win. Because we haven't even tried to build that API yet, I don't know if that's the right API for Rust or not. Chris?
So you mentioned earlier the idea of template expansions causing a lot of duplicated code that the linker has to clean up. I mean, that problem is actually more general than that in C++ because you also have all the weak link once ODRs. And have you given any thought about how you might be able to do a linker service that could then drive and provide information to the compiler to reduce that?
Yeah, so this is an idea that's been bounced around, which is the idea of a pipelined linker. The fact that the linker runs and it loads all of these object files way after the compiler has produced them. So even if you don't even think about the fact of the data structures it's building, it's terrible for the file system cache because you wrote that object file, then you didn't touch it, then you read it again. And in theory, you could spin up the linker as soon as you write the first object file. You could tell the linker, hey, go ahead and parse your data structures out of this, and then go forward. I think, but there's no build system that can drive it that way. So whether you would want to use this for things like link once ODR, I think the real trick of the more complicated directions like that is how you manage reproducible builds. Because I have a strong belief that you shouldn't do anything where you've given up reproducible builds. And so you want to phrase the problem as, can the linker compute some kind of incremental data structure effectively that we can use? You don't want to just say, have I done it once this build? And I think I don't know how we would do that yet, mostly because we don't have an architecture that we could even think about it in.
One more quick question. All right, then let's thank our speaker.
All right, thank you.